Ever wonder how a robot decides which path to take? Or how a game AI knows the best move without being told? Behind the scenes, there's a powerful idea at work. It's hidden inside one of the most important equations in reinforcement learning, the Bellman equation. In this video, we're going to break it down in the clearest way possible. You'll see how it works, why it matters, and how it shapes the intelligence of everything from game bots to autonomous cars. Stick around, because by the end, you won't just understand the Bellman equation. You'll see the world through it. Pause for a moment and reflect. How do you make a decision? Would you attend a free party? Would you engage in something illegal that could land you in jail? Would you take on a task that promises financial gain? Each time you act, whether consciously or unconsciously, you evaluate the potential benefits or losses. This evaluation is what guides your decision-making. You weigh the possible rewards, whether financial, emotional, or otherwise, against the penalties you might incur. Your actions, in essence, are dictated by the rewards you anticipate or the penalties you seek to avoid. This fundamental principle is precisely what the Bellman equation quantifies. Every decision begins with a state. A state represents your current situation. It could be your location, financial status, health condition, or any other defining factor. This applies not only to humans but also to robots and video game characters, collectively referred to as agents. When an agent state changes, it signifies a shift in one or more variables, typically triggered by an action, such as moving from one place to another, making a purchase, or taking a specific step. Each state comes with a set of available actions. Some actions are possible, while others are not. For example, an agent with 0 credits cannot buy anything, making the purchase action unavailable in that state. Decisions are driven by the expectation of future rewards. The term perceived is crucial here. Imagine standing one step away from a treasure worth $1 million. Your position is nearly as valuable as the treasure itself. But not quite, because you have not yet claimed it. If you were 10 steps away, your position would be worth significantly less. But by how much? This is where the discount factor comes in. The discount factor, typically set around 0.9, reduces the value of future rewards as they become more distant. If you are one step away, your position might be worth 0.9 times $1 million equals $900,000. If you are 10 steps away, its value drops to 0.9 to the power 10 times $1 million or $348,000. Now, consider multiple rewards at various locations. If there are 3 treasures, one worth $1 million at a distance of 10 steps, another worth $1,000 at 2 steps, and a third worth $10,000 at 5 steps, then the value of your current state is the sum of all these discounted rewards. V equals 0.9 to the power 10 times 1 million plus 0.9 to the power 2 times 1,000 plus 0.9 to the power 5 times 10,000, which is equal around $350,000. Even though the $1 million treasure is 10 steps away, it still significantly impacts your decision-making. However, if it were 100 steps away, its influence would diminish considerably. Thus, the general formula for the value of a state is V equals gamma times the sum of rewards, where gamma is the discount factor and R represents the individual rewards. The value of the current state accounts for the reward in that state plus the sum of future discounted rewards. Let's call it V0 equals R0 plus gamma times V1, where V1 is the value of the next state. So far, we have assumed a deterministic world, where taking an action in a given state always leads to the same outcome. However, real life is not that predictable. Consider an archer aiming at a target. There is no certainty that the arrow will hit its mark. The outcome is probabilistic. In reality, taking an action in state S does not guarantee reaching a specific state S prime. Instead, there is a probability distribution over possible landing states. Similarly, rewards are not always fixed. Achieving the same state twice may not yield the same reward. To account for this uncertainty, we adjust our equation. Value of S equals sum over S prime times probability of reaching S prime times the term R plus gamma times value of S prime, where P of S prime is the probability of reaching state S prime and obtaining reward R prime, given that the agent started in state S. In practice, computations do not iterate over all possible states, only those that can be reached from the current state. If a state S4 cannot be reached from S1, then its probability is 0, making it irrelevant in the calculation. However, the mathematical notation shows that the iteration is done over all possible states, and for each unreachable state, the probability P will be 0. This seems confusing at first, but it is written that way to make the equation more compact. While coding, depending on how you define your states, you usually don't loop over all states, but over the reachable ones from a given state. The value of a state represents how beneficial it is to be in that state. Consider an example. From a given state, if you move right, you gain $100. If you move left, you lose $100. Now, assume both actions, right and left, are equally likely to occur. In this case, the expected value of the state would be 0, since the potential outcomes cancel each other out. However, if you're allowed to choose your action, you'd obviously choose to go right and earn $100. This highlights an important point. The state itself isn't the only thing that holds value. The actions taken within that state matter too. This is where Q values come in. Q of S and A represents the value of taking action in state S. It accounts for both the immediate reward and the future expected rewards. Formally, the Q value is defined as the immediate reward received from taking action in state S plus gamma times the sum of each state value multiplied by the probability of reaching it. A policy determines which action an agent should take in a given state. For instance, if an agent is in a burning building, should it take the elevator, jump from the 10th floor, use the stairs, or wait for help? Fire safety guidelines serve as a policy, instruct people to stay put and wait for assistance. Policies are learned over time, through experience. In reinforcement learning, the objective is to find the optimal policy, meaning the one that maximizes expected rewards. Mathematically, a policy is a function that assigns probabilities to each action in a given state. Just as some states render certain actions unavailable, policies assign a probability of 0 to impossible actions. Imagine a video game scenario where an agent can move left, right, forward, or backward but cannot jump. In this case, pi of jump at state S is 0. By iterating over different states and actions, reinforcement learning seeks to refine policies until they yield the best possible outcome. Imagine an agent that needs to run and jump over obstacles to earn rewards. If it fails to jump in time or with enough force, it loses. As the AI experiments with different actions, it discovers that jumping at the right moment and with the right force leads to success. Over time, it begins to assign a higher probability to the jumping action when the agent is in a state where the distance to the obstacle and running speed are just right. In those optimal situations, the policy, represented by pi, favors jumping more strongly. This process of adjusting the probabilities of actions based on experience is what we call learning a policy. We have established the concept of the state value function V of S, which represents the expected cumulative discounted future rewards starting from state S. Recall an earlier example where the value of a certain state was 0 because the agent had a 50-50 chance of winning or losing $100. However, suppose the agent adopts a policy pi that prefers the action go right 80% of the time, and the rest 20% will be go left action. Under this new policy, the expected value of the state becomes 54. This shows that the policy pi directly affects the value function. By biasing the action selection toward more rewarding outcomes, the policy increases the expected value of the state. Now, let's try to derive the general formula using policy pi. Starting with a state S, we suppose we have two possible actions A1 and A2. Performing A1 will land us at states S1, S2, or S3, with different probabilities. Performing A2 will land us at states S3 or S4, also with different probabilities. So the V of S becomes the probability of taking each action times the sum of the probability of landing on each state multiplied by the term reward plus the discounted value of the target state. Always imagine the tree-like graph of the previous slide. It will make it easier to grasp the whole notion. Let's simplify by isolating some of the terms. Let f of s comma a be the sum of all probabilities of landing on a certain state provided that we are at state S and took action A, times the reward plus the discounted value of target state. In this formula, we have covered all the possibilities starting from state S and by taking any available action at that state. To prove that, set f of s comma a1, the probability of reaching state S4 is 0. If we try f of s comma a2, the probability of reaching state S1 or S2 are 0. So we can see the terms of the previous slide. Now, let's factor in the f of s comma a with the main formula of v of s. We can see that we can group the policy pi and the term f of s comma a under the same sum sigma. Because the f of s comma a will depend on the action A, depending on A, some of the probabilities will become 0, and the formula will remain the same as previously. Finally, by expanding a little bit the previous formula and replacing f of s comma a by its expression, we get the main Bellman equation. As you can see, despite its cryptic appearance, the Bellman equation is not as hard as it appears. From now on, this equation won't be a mystery for you. Keep in mind this tree-like graph. It will be crucial for understanding the whole concept. At its core, decision-making is about maximizing expected future rewards while accounting for uncertainty and constraints. The Bellman equation serves as the mathematical foundation for this process, balancing immediate rewards with long-term benefits. Whether applied to financial investments, robotics, video games, or everyday choices, this principle underpins intelligent behavior across domains.